let's get started with Unit 2 of the course. So we're done with solving algebraic equations. We did linear and nonlinear equations. And those are gonna be very, very useful. Okay, not in window, hold on. Okay. All right. So we started the course with preliminaries and the error analysis. Next, we talked about solving algebraic equations. They were both linear and nonlinear. We studied linear solvers, nonlinear solvers, systems of equations, both linear and nonlinear. You use fsolve, and you have the tools for lin algebra and inverse. That's great. We have those tools under in our tool belt. And lo and behold, in everything we're going to do from here onwards, we are going to be faced with linear and nonlinear systems of equations. So that's why we cover those at the beginning, so that we know how to solve them so we can proceed further. Chapter 2, or Unit 2 in this course, has to do with data analysis. I don't call it data analysis because we're not doing statistics, really. It's more like looking at data and doing a poor man's job of trying to describe the data. So I call it curve fitting. And technically, that's what it's doing. It's trying to get some data points that are not a curve and trying to put a curve in between the points so that you can see a pattern emerge. There's two pieces in curve fitting. We will talk about interpolation and regression. Now, here's the challenge. I want to move regression. So my vision for this course and statistics is to call this Data Science 1 and Data Science 2 eventually. And my plan was to move regression analysis into statistics next spring. Okay? So you're going to be with me in statistics next spring. Sorry. And so we will do more regression analysis there. But despite that, we can do some basic regression analysis here, and without all of the statistics behind it. Okay, we'll just do the mechanistic way, understand how regression works, so that when we had statistics, we can focus on understanding the science of data, or how we think about data. Okay, so we will do regression analysis here, which will be part 2 of curve fitting. But part 1, we will start with interpolation. And my learning objectives for this year, again, what's shown in red is depending on if we have time, we'll cover it. If not, we don't have to cover it. But at the end of this chapter, you should be able to define what it means to interpolate data, derive the system of equations that one needs to solve to build what's called a polynomial interpolant, list the benefits and limitations of first-order interpolants, benefits and limitations of high-order interpolants, calculate by hand an interpolated value using a linear interpolant, identify which points are best used with linear and quadratic interpolants, list the conditions for what we call cubic splines. You've probably heard that word. If you're doing Adobe Photoshop or something, it tells you use splines. So we'll understand what splines mean, cubic splines specifically. Only the conditions, though, and how many unknowns there are. We're going to go back to these, what we know and what we don't know. Then use built-in Python functions to perform polynomial and cubic spline interpolation, and show how linear interpolation works in 2 dimensions. Only going to show it, and then create Python code to do 2D linear interpolation. And if time permits, and I think I want to cover this year, is to do interpolation with what we call arbitrary basis functions. So that will really expand your mind on what you could do with math, and nonlinear interpolation. Now, in all of those, there will be systems of linear equations and systems of nonlinear equations. We know how to solve those. We close the books on those. In this chapter, we will mostly be using built-in tools in Python to do the interpolation. But because you're an engineer, you need to understand the machinery behind it, because you will be a creator of those tools in the future. Okay. So I don't have a movie for you on interpolation. If you find a movie, it's really hard to find anything on interpolation. So I don't have a movie. I'll give you some data from my home in Sandy. But let's start with the motivation. So oftentimes, if you've done undergraduate research, some of you are doing some undergraduate research, perhaps in one of the labs of the faculty here, you're doing experiments. You go collect data. Say you collect this value at this time, another value at another time, or you collect some value of the pollutant, let's say, or the concentration of something versus the volume, and you change the volume, you measure different concentration, and so on and so forth, right? So you have discrete data at specified intervals of something. Okay, could be time, could be position, something. Okay, and you oftentimes need to interpolate. So, for example, like right now, I know the temperature is like 56, and what is the temperature right now? Let me see. It's telling me it's 52 and it's raining, okay? And let's say, what was the temperature? And the temperature at 10 o'clock was 49. What was the temperature at 12, for example? You're going to interpolate, you want to interpolate the data to see what's going on. So the idea is simple, is we take the discrete data and we fit a polynomial function in the data. In other words, we connect the points of those discrete data with a mathematical formula that looks like a polynomial. It could be ax plus b. Is that a polynomial? Yeah, it's a first order polynomial. Or ax squared plus bx plus c. That's a quadratic. Or a cubic, ax cubed plus bx squared plus cx plus d. You connect the points with one of those formulas. Now you have an analytical formula that you can use to evaluate at any point in between. Does that make sense? So you use the discrete points. That's the idea we're trying to cook together. You connect the points with a function that you know an analytical formula for. And then you can evaluate the analytical formula at any point in between. Okay? That's the idea. All right. So let's start with an example. This is some data I collected from our home in Sandy in August. I think this was 2018. And it starts at midnight, 0, so in hours, so going to 24 hours, right? Starts at 75 Fahrenheit, then starts dropping, 6 in the morning, and then the sun rises, okay? Then starts warming up, goes to 72, 79, 86, kind of almost midday here, but then really the peak temperature is usually around 4 o'clock. We always avoid going to the zoo at 4 o'clock. We try to go in the morning or later. And then, in the evening, sun sets, you start cooling down, and then the cycle continues, okay? So those are the data that we have, right? It's not weird. Temperature versus time of day. Now, if you don't know that yet, this is called the independent variable, and this is called the dependent variable. Temperature versus time of day. Okay? This is the response variable to the time of day. Okay. Now my question is, given these data, what would you say, what is your best guess for the temperature at 1 o'clock or 13 hours? Give me your best guess. Pardon me? 87.5. Okay, how did you get that number? Okay, so 13 is in between 12 and 14, and like right in the middle. So what did you do?
I guess you could say I interpolated.
No, tell me what you did exactly. You like, what did you do in your head to get 87.5?
I guess I just looked in.
Just visually spotted that. Okay. By 2. So you took the average, right? Yeah, that's fair. What else would you do? Do you think the temperature at 13 o'clock would go up to 900 and then come back down? Unless there was like an asteroid event or like a solar eclipse, right? The moon is in front of the sun. You get the sudden drop in temperatures and then goes back up. None of these happened on that day. Okay, so, clear, reliable trajectory. Yeah, I think that's a very reasonable and the best guess we could make, right? Take the average of those 2 points. Okay, great. At 1 o'clock, the temperature is likely to be the average between the temperature at 12 o'clock and the temperature at 14 o'clock. So you get 87.5 because it's like right in the middle. The best guess would be the average of those two. Okay? So now, what is the temperature at 1:17 p.m.? In other words, at 13.28 hours. So now you're not in the middle. I'm asking you for the temperature not in the middle, but slightly skewed to the right. How would you do that? Michaela. Okay? So your colleague is saying, hey, let's draw a line between 86 and 89, a straight line. Okay? Because we know nothing of what's happening in between those 2 points. Maybe it's just we put a straight line. In reality, the temperature might be changing a little bit differently. Might not be just straight line, could be changing cubically or quadratically, I don't know. Right? But in the absence of any other information, a straight line seems like a reasonable guess. So draw a straight line and intersect that straight line. Okay, so that's the straight line. And intersect it with, so if you get the formula of that straight line, you can evaluate it at 13.28 hours. Agreed? Okay? So draw a straight line between 86 and 89, intersect it at 13.28. In other words, that line is going to have the formula, as your colleague said, mx plus b. M is the slope, you can evaluate that. B is the intercept, where it's crossing the x-axis. And now you have a formula for that line in terms of x or time of day. Once you have that formula, once you have m and b, you can just plug in 13.28 and get the value. Okay? Okay, so go ahead and do that. Straight line between these 2 points. The formula for a straight line is mx plus b. M is the slope. You can easily evaluate the slope. B is the intercept. So just evaluate that line at any one of those points. Okay, and you get the intercept. So get me the formula for that line. Okay, so now evaluate it at 13.28 hours, right? So I would write it as temperature equal 3/2 times time of day, right? Times lowercase t, let's say, in hours, right? Plus whatever. And then at 13.28 hours. Y equal mx plus b, that's the formula for a straight line. The slope is rise over run. So 89 minus 86 over 2, right? That's the slope, rise over run. And the intercept, you just evaluate that straight line at any one of those endpoints to get b. Okay? Got a temperature, 87.92. Okay? Okay? If you're stuck, raise your hand. And I'll come and help you. You got it?
No,
A little stuck?
I'm still. There's a slope of 1, right? Or am I not?
So 89
Sorry.
minus, no. 89 minus 86,
It's 3.
3 over
Yeah.
2,
Why
because 12 and 14. The rise is 3,
the-
right? And the run is 2,
Okay.
right? Yeah, so 3 over 2 is the slope,
Okay.
okay?
So,
So that gives you the slope. So you write y equal 3 over,
so yeah, 3
Okay.
over 2.
okay. So now you need the intercept. How do you get the intercept? So you know two values. You know
Yeah.
the value at 12, which is 86, and you know the value at 14, which is 89. You can use either one of those
Okay.
facts to get B. So just simply plug in 12 and y equal 86, and then you can get B.
Well,
Okay? Let me show you.
yes.
So we wrote y equal 3
Yeah.
over 2 x plus B.
Okay.
Okay? Now, at x equal 12, y is equal what? 86. 86. Therefore, 86 equals 3 over 2 times 12 plus B.
Oh,
Right?
I just-
Okay. Stay positive, stay positive. You guys got it? Yeah. Perfect. Perfect. Okay. You got it? Okay. Yes.
Is this right here?
Sure. Yeah. Okay. Okay, let's do this. Let's break it down. Let's break it down very simply. So we're trying to find this straight line, okay? And we're trying to find the formula for this straight line and then evaluate it at 13.28, okay? So connecting the points, that's wrong here. What is connecting the points? Sorry, there's a typo here. 12, 86, and then 14, 89. Okay. All right. So the equation for a straight line, in this case, T of x, or temperature, as a function of x. X is really time of day. I could have used like lowercase t if you want. Equal mx plus b. We know m is the slope, and t is the temperature. The slope is simply the rise over run, which is 89 minus 86, right? That's the rise going from this first point to the next point. It's 3 over 2, which is 1.5. Okay. Now, to find the intercept, b, you simply, so you plug in m over there in the equation. You have t equal 1.5x plus b. How do you get b? Simply evaluate t at any one of the endpoints. T at 12 is 86, and t at 14 is 89. So when you plug those values in, you have one equation and one unknown, and you get b, right? So let's say you take t at 12 equal 86. So that's m times 12 plus b. But m is 1.5, so you get 18 plus b. Therefore, b is 86 minus 18 equals 68. And you get the same answer if you do it at the other endpoint, okay? So now we have a formula for that straight line that says the temperature between 86 and 89 varies according to, in our proposed change for the temperature, which is just linear, a straight line, looks like 1.5x plus 68. Okay? Now you can take that and evaluate it at any point in between 86 and 89. Agreed? You have a formula, continuous formula, whether at 13.28 or any other point. Okay, how can we do a sanity check here? What if we evaluate it exactly in the middle at 13? Would it give us the average? You should check that. And it should give us the average, because the average is part of this straight line averaging thing, okay? Okay, so now you substitute x equal 13.28. You plug it in here, and then you get a number for the temperature. Sanity check, does it make sense? Yeah, it's in between those 2 points. We drew the straight line. If you get a value that's 100, then you're in trouble, because the straight line shows you that all the values are between 86 and 89. If you got some other value, then you have something wrong in your equation, right? Okay. So now the question, what values of hour or the x-axis is this equation valid for? Can I apply this at 11 o'clock? Why not?
May not have the same slope.
If we're doing straight lines between those different points, we probably don't have the same slope between these 86 and 89 and the other 2 points. And in fact, that's true. When you go to 12, 11, and 10 o'clock, you have an entirely different slope. Okay? So you cannot take that line and apply it outside the bounds where you applied it for. Okay? That's why we call it interpolation. You're finding an approximation in the intermediate points. If you go outside bounds, that's called extrapolation, and it's a bad idea. You don't do that. Okay? With regression, you can do extrapolation, but we will talk about that later. Okay, good. So we did that, right? And you know what? You just did linear interpolation. Okay? You just did linear interpolation, but in kind of like this awkward, interesting way. We want to generalize this now. Okay? So in general, given any 2 points, so now I'm abstracting this. And I always use x for the independent variable and y for the dependent variable. I could swap them to mess with you, and that shouldn't matter. But from here, in the next few lectures, we're using x to designate the independent variable. That's the variable you have no control over, essentially. It's not a response. Time, space. You just say, I'm from here to here, but this is space. But the response of the temperature depends on 100 other things, okay? So the dependent variable in this case is y, and the independent variable is x. And linear interpolation says you're given these 2 pairs, x1 and y1, so temperature at the first time of day, temperature at the second time of day, or these data pairs, x1, y1, x2, y2. You know those numbers. You know those values, they're given to you. And you're asked to find this straight line, y of x equal mx plus b. Now, notice I'm using red to designate unknowns in this case. Because this equation, although x is going to be an unknown, but that's only for later. Because right now, I need to find what m and b are. So as far as I'm concerned right now, and the slope and the intercept are my unknowns to build this straight line. Okay? So given 2 points, x1 and y1, x1, y1, x2, y2, we can derive the equations that we need to solve to find the slope m and the intercept b. And by definition, the straight line must pass through those points. It must pass through. That's the definition of interpolation. Okay? Okay. So we have two unknowns, m and b. What does logical math theory tell us? To find a and b, how many m and b, how many equations do we need? 2 equations, right? So we have 2 unknowns, we need 2 equations to solve for m and b. Okay? How do we get those 2 equations? We kind of did that, but indirectly, okay? Because you thought something about the slope and b. Well, you already have information about the first pair and the second pair, and because the straight line must pass through those 2 points, then we can simply evaluate that line, that equation at those 2 points. And that gives you your 2 equations. So if you evaluate that formula, yx equal mx plus b at x1 should give you y1. So y1 is mx1 plus b, and y2 is mx2 plus b. Agreed? Do you know y1, x1, y2, x2? Yes, they're given to you. That's why I'm showing the unknowns in red. Now note what happened here, and remember when I said the variable of interest, and I told you we're going to change the meaning of those. in the nonlinear lectures about nonlinear equations, we thought of x and y and z as our unknowns. But then still I told you, what is the variable of interest? Does A show up linearly? Does X show up linearly, nonlinearly, etc.? Over here, my variables of interest are M and B, not X and Y, because the X1 and X2, Y1 and Y2 are just numbers. You know them. So in these two equations, M and B are your unknowns. Do they show up linearly? Yes, they show up linearly. This is a system of linear equations. Interpolation, linear system of equations, absolutely. Wait until we get to a 10th order polynomial, see the mess you're going to get. Okay? But we go back to linear systems of equations. The fact that this is a small system of equations, we can solve it exactly, doesn't take the fact that it is a system of linear equations. Okay? Keep that in mind. Keep in mind that the critical piece of information is that we couldn't do this if the straight line did not pass through x1, y1, and x2, y2. We couldn't do this. This is because of this fact that the line must pass through these 2 points. Okay. So then you solve this system of equations. Luckily, we have like an exact formula, and then that's your formula in general for linear interpolation or interpolation to a straight line. Okay, interpolation to a straight line between 2 points. You have 2 points, x1, y1, x2, y2. Find the y value or the dependent variable at any point in between. So this gives you that formula for the straight line. It looks different. Okay, it looks a little different, but it's the same. If you compare the two with what you did by hand, finding the slope and the intercept, they're identical. But we always write it in this way. That's just a standard way of writing the formula for a linear interpolant. Okay? The advantages is that it's very easy to use in homework and exams. You know, back of the envelope, you're in an airplane and you're like, you have a brilliant idea to cure cancer or something, and you need to interpolate data between, I don't know, 2 cells or something, and do a linear interpolant. You can use this formula, get a rough idea of what it does. Now, understand this formula. What are you doing in this formula? You're given x1, x2, y1, and y2. You're trying to find the formula for the straight line here so that you can find any value in between those 2 points. So on the right-hand side, x now becomes your unknown. Okay? X becomes your unknown, and y is the response to that x. So you can take this, apply it to the temperature problem we did previously. You'll get exactly the same result. But it's not very accurate for nonlinear data if the data in reality between those 2 points varies in some nonlinear way, which could be with temperature perhaps, okay, then you're not very accurate. You're putting a straight line whereas the data is truly sinusoidal maybe, or cubic. Okay, so you're not going to be very accurate. That's a mystery that it's really hard to figure out when you have experimental data. The only thing that will work for you is knowledge of the system you're dealing with. If you think your system behaves in a very nonlinear way, then don't put straight lines. We will learn how to put quadratics in between. Okay, we'll do a better job at getting more accuracy. Okay? All right. I love linear interpolation because it's simple. And when you have very closely packed data, so let's say you're measuring temperature every 10 minutes, okay, or every 5 minutes, right? Then you have the data is very closely packed. Even if the behavior overall is nonlinear, between very close points, a linear approximation is a very good idea. Okay, so when you have more sampling, you're measuring the temperature at more intervals, then yeah, using linear is a really good idea. It's not a bad idea. It's not that bad. Okay. Now you can do linear interpolation for a large data set. So let's go back to the temperature, which will be on your homework assignment. We'll deal with another data set right now. But let's say you take that temperature data for the entire day, and now you want to do linear interpolation between any 2 points, not just 86 and 89. You want to build that interpolant for every pair of points, right? So there's a trick to do that. Here's an example of another set of data that we will work with next. It's density of air versus temperature. Okay, and we know that at high temperatures, air gets lighter, right? It starts rising, the density gets lower, and at low temperatures, the molecules tend to cluster together, right? So they increase the density. And indeed, this is what this data plot shows. At 100 kelvins, the density of air is about 3.5 kilograms per cubic meter. You know, as you get to like room temperature, which is 1.225, somewhere around here, density of air. And then as you raise the temperature, it looks like this, okay? And slopes down and then flattens out. At 1,000 degrees, about a half kilogram per cubic meter, okay? So obviously, this data is nonlinear. It's curves and kind of flattens out, etc. And what if I want the temperature between, you know, at 107? Okay, you could say, I'll put a linear interpolant here. Let me run the calculation. I'll get back with you, and you do that. Or a temperature, the density over here at 425. Okay, so you could go and pick these 2 points, draw a straight line, find the formula, and that works great. Okay, but there's a cleaner way of doing it in Python specifically. So by hand, there's no way around this. You have to pick the 2 points around the point of interest, draw the straight line, get that formula, and evaluate it on the calculator. But programmatically, what we can do, we can take this entire data set, and this is unique for linear interpolation. You can take that entire data set and feed it to Python and tell Python, you put a straight line between every pair of points, and I'm just going to ask you to give me the answer for any point on the x-axis. So what it does internally, it draws a straight line between these 2 points, these 2 points, these 2 points, and so on. So let me show you. Okay. It draws a straight line between each pair of points and stores that information internally in its memory. And then when you go and say, I want the temperature here, it says, oh, this is between these 2 points. Here's the formula. I'll give you the answer. Or the temperature here. It finds this straight line because it did all of that. It stored it internally, like one line of code. We will see that. Okay? So this is very convenient, and that's really unique for linear interpolation in Python, as we will see later. So to do this in Python, we're going to go back to NumPy. And NumPy has this built-in routine called interp. Okay? So you can import NumPy, or from import NumPy as np, and you can say np.interp. And this is what it looks like. I'm writing here as ye equal numpy.interp. There's three arguments at least for that interp routine: xe, xi, and yi. Okay. Now, xi is the known independent variable entries. So those are all the x input. So I stands for input. All of the input values on the x-axis. So those are the discrete data that you're given. Okay, so 100, 200, 300 for the temperature plot, for the density and temperature thing. Yi are the known dependent variable entries that you are given. So if you go back to the previous one, so those would be the y values of the density values. Okay, those would be the density values. Xe is the value where you want to interpolate. So think of input and exit, I guess, ye, I called it, xe. It's the value where you want to interpolate. So what this interp does, it takes all the data input, xi and yi, and it figures out how to do the interpolation at xe. Okay, at the independent variable of your choice, the value of your choice, and it outputs the data as ye. So we're going to give it xi and yi, and those are the experimental data that you have, for example. And we're going to ask it to interpolate the values at xe. Think of the independent variable, and it's going to give you a result ye. Okay? So go on Canvas, and you can download this notebook. It's It's under, if you go in modules and interpolation, you will find it, or under files, activities, interpolation. It's called interp activity 1 with gaps. The reason I had to do this because I don't want you to type the data by hand. I already typed the data and put it in the Jupyter notebook. So go ahead and download that notebook, and we will work together on it. Okay. You can probably search for it or just find it under files, activities, notebooks. So let me see. Okay, so the notebook with gaps is this idea I implemented a while ago. I stopped doing it as much. So I give you a preloaded notebook with a discussion, and I put question marks in the code for you to fill in. Okay? So if you've downloaded the notebook, open it and start reading while I download it here on my end and can work with you on it. Okay, it's called interp 1 activity with gaps. Okay. Okay, so start reading the notebook. There's a few questions at the beginning. I think you can answer those. Gaps. Okay. Okay. Window. Finally. I thought I downloaded it, but now I recognize that I'm getting old and forgetting things. I downloaded it on my office computer. Okay. So this is the notebook. It's got the boilerplate already for you, and it has the temperature and density data. Okay. So the temperature data, because it is so structured, I created it as a linear space from 100 to 1000 with 19 data points. Okay, so 100, 200, 300, 400. Okay, and I had to manually put in the density data for a row. Okay, so if I execute this cell, see what I get for the temperature: 100, 150, 200, 250, and so on. Okay, and the density data. Okay, the first thing to do when presented with data is to plot it, as we've always discussed, or just get familiar with it. So here, go ahead and plot the density versus temperature, because we're treating the temperature as the independent variable, and the density is our response or dependent variable. So go ahead and do that. So you should see the same pattern that we saw in the slides. So this would be T on the x-axis. And so let me turn. Sorry, I have to turn my back to you, but Can't teach you otherwise, okay? And then row, put \row and then tab. If you can't type row, just copy it from here or change the name of this, call it RHO, okay? And then you plot this, okay? All right, so KO means black circles, okay? It's very important, I cannot stress this enough, when dealing with discrete data, do not draw lines in the discrete data. Keep them as a scatter. So when you draw lines, you assume that the data is varying linearly. So in fact, if you were to do KO and put a dash, which will connect them with lines, you're assuming a linearly changing. What matplotlib does, it assumes a straight line between the data points, okay? Which is like it's doing linear interpolation. Now, if you want to do this for the plot to look nicer, do the lines, but make sure you also put the disks, the scatter, so that you stress that your data is discrete and not continuous. This data is discrete. It's not continuous. So make sure you put the circles here, connect them with a line. It's okay, I'll allow it. But if you're truly looking at, when we're dealing with discrete data, we don't put lines between them, okay? So you can keep this if you want. That's okay. We're going to do linear interpolation anyway. So, and I say here, always plot a scatter without connecting the dots. However, to show what linear interpolation, I guess I repeat myself every year. Okay. So then I'm going to do same thing, T and row, and then I'm going to put K, O, and dash. Okay. That gives you. Okay. So this is actually what linear interpolation would look like. Any plot that Python is producing or MATLAB, when you put a dash, dash dot between them, it's drawing straight lines between each and every 2 points. Okay? That could be misleading if the change between the points is not a straight line. So be careful when you draw a straight line on scattered data or discrete data. Okay, so let's start now with doing linear interpolation, but for a single value. So I'm going to move the window here, this thing. Remember, this was our formula for our interface for how to use Python to do linear interpolation. Let me hide these things here. Okay, slide only. Okay, so now I want to use the interp function, and I already imported interp from here, from NumPy import interp. Or you can do np.interp, it doesn't matter. Okay? But here I want to use NumPy's interp function to find the density at t equal 132. This should be Kelvin, actually. This should be Kelvin. Okay? Okay, go ahead. So you have these 3 question marks you need to fill in. This is where you want to interpolate to. These are the inputs, and the last 2 are the input independent and the input dependent variable. And you can give the entire data set. So as you can see here in this description, xi and yi could be the entire data set. Just give it the entire data set. Python will know what to do. Okay, what did you get? A bunch of numbers. So at 132, so that's going to be between 100 and 150. So it's going to be between these 2 points, these first 2 points, right? If I go back here in the slides, it's going to be between these 2 points here, between whatever, 3.5 and 2.3, let's say. It's going to be between these 2 points, right? So what did you get? Pardon me? 2.7. That kind of makes sense. It's between those 2 values, right? Okay? So if you're still struggling with this, the first the first argument is going to be where you want to interpolate. We want to interpolate to t equal 132. So I'm just going to put 132. 132. The second one is going to be the independent variable inputs. So that's going to be what? Temperature. Correct? So I'll put all of t. T was already declared here as an array. Great. All the values for t. And then in the second one, all the dependent variable inputs. So that will be what? Rho. And if I do this, it gives me 2.775528. Okay? Yeah.
So, if I'm correct, for the first slot, it's what we want. Then the next slot is what we is the independent variables,
Input.
independent inputs, and the last slot is the dependent variables.
Mm-hmm.
Okay.
Yep. And if you're confused, you can look at the function signature, go to the parentheses, and press Shift-Tab, and it explains to you the x coordinates. XP is the x coordinates of the data points, etc. And then FP, it's kind of weird, the y coordinates of the input data points. My explanation is cleaner, I think. So input independent variables and input dependent variables. Okay. Okay. So make sure you get all of that. Okay. All right, so now, so we did this for a single value. Okay, good. It gave us 2.775. Okay, and that kind of like, okay, so what? Now, instead of finding it for a single value, I want to find it for a bunch of values. 123, 251, 443, 599, 602, and 899. What do you think we should do? Well, yes? Yeah, because you were first. Yep. Was that what you suggest, Gretchen? Yeah. Yeah. So there's no reason, like imagine they created this interp function. It takes an entire data set for input, entire data set for output, and only does interpolation at a single point. That would be like the dumbest design ever, right? I would expect that XE, I can put a bunch of values at XE, not just simply one value. I want to interpolate this data at 50 other data points. I can do that. And indeed, in my description, I say known values where you want to interpolate. So that's what we're going to do here. XE is going to be numpy.array. And I'm just going to straight copy these out from here. Okay. So now I'm interpolating. I'm taking this data set XIYI, and I'm going to interpolate it at each one of those points. Okay. What do you think it's going to return to me? First, it's going to return, is it going to return a single value, two values, an array? What is it going to return? Okay, containing what? Pardon me? The interpolated values. Okay, in the order these were given. So it's going to give us the density at 123, the density at 251, the density at 443, and so on. Consecutively, in that order. Okay, so I'm going to put XE here, and then T, and then rho. I didn't change the inputs, the input data set. It's still the same, except now I'm asking it to interpolate at more points. Okay, there you go. It gave me an array, and it contains a bunch of values. 2.99, 1.39, 0.79, 0.58, and so on. What are those values? They are the density values, the interpolated density values that don't exist in the input data. They do not exist in the input data. But they're interpolated at those temperatures. So this is the density of air. 2.99 is density of air at 123. 1.39 is the density of air at 251. 0.38 is the density of air at 899. Okay? 1 to 1. It's the same size as the input. Okay? Now what is cool is that you can actually plot these points on top of the original data to see where they're located at, right? It's great to visualize things. It's a blessing in science that, and those who do math and computing, it's a blessing you can visualize things easily, okay? Like quantum mechanics, they can't visualize a thing. They have to come up with like these crazy theories that things can be here and there at the same time and all of that, which is amazing, but it's hard, it's just, you can't visualize it. Okay, so we can now plot the interpolated points as red squares. So what are we going to do here? So we're going to plot the original data, which is rho versus t with black circles connected with a line. But next, I want to plot these temperatures, 123, 251, etc., and their corresponding interpolated densities, and mark them as red squares on the same plot. Okay, so what should we put here? X, E, Y, E. Bravo. Okay? X, E, Y, E. Make sense? X, E are the independent points we want to plot. So Y, E versus X, E. So when I do this, a miracle happens. I get these red squares over here. It's gorgeous. It's consistent with what we learned so far. First, I see the straight lines between each pair of points. And I see the values that we interpolated at. So the first one at 123, and this is the value, 2.99. The second one, the third one, and so on. And they're like lying in between, correctly in between each pair of points. So Python knows what it's doing. It's great, very simple. Give it this data set could contain 1 billion points. Yeah, just do it like that. It's really great, very simple. Okay? Okay, good. So let's see what's next. Now create a linear space of 100 points for the temperature and interpolate to those points and plot the data on top of the original data. So instead of doing, so first we started with 1 value for temperature. Next we did like, what, 6 values. Now I want to do 100 values between 100 and 1,000. Just equally spaced values. I want to interpolate at those. Why? Because we're just making up this problem, right? Okay, so let's create the lin space. What is going to be our first point? It has to be the smallest value in the data set. It cannot be any lower because we are interpolating. Okay, so our bounds are going to be between 100 temperature and 1,000. We can't go above or below. It's not interpolation anymore if you go outside the bounds. So let's create a lin space for independent variables from 100 to 1,000 and put 100 points in between. So that's what lin space is going to do for us. Okay? And then I'm going to interpolate t and rho to those new xe values. Great. So if you're in doubt, you print it, print xe if you want. And then you see all of the new temperature points. And then you see the plot. Look at that. It's like exactly what we expect. All the interpolated points fall within their respective straight lines. And not only that. Look at this first point. The temperature is 100. Which belongs to the original data set. What value should it return? The interpolated value. What should it be? So pardon me? I heard a voice. So the input data starts at 100 and it has a temperature at 100, a density at 100, okay? In the interpolation, I'm also asking for it to interpolate to 100. What value do you think it's going to give me?
Will it just give us the original value?
Yes, the original value. So that's the definition. Is that what you said, right?
Yeah.
Yeah. is going to give us the original value in the original input data set. Because by definition, these straight lines have to go through the input data. And so if you ask the straight line, give me the value at the input data, it better give you that input data. Look at that point. It's like it's on top of that black line. Same for this last one. It will give you exactly that initial value, because that's how we evaluated the straight line. We said y1 at x1, y at x1 equal y1, y at x2 equal y2. So by definition, by construction, the interpolant is going to return the same value that was input to it. Okay? So that's always a trick question. Give you a bunch of data points and ask you what's the interpolated value at that point. And people start calculating, etc. You don't have to calculate. It's in the input data. By definition, the interpolant has to go through each and every point. So it's going to return those exact values in the input data. Okay? If you don't believe me, try it. Okay, so you can do interp at 100 for t and rho. Okay? It gives you 3.5562. Now, what is the first value in rho? 3.5562. Not even round off error. Okay? Because it was built like that. What is the second data point? 150. Okay? So that's going to be the second data point. Look at that. It's the same exact value. Because it's built that way. It has to go through the input data. So when you ask it to give you a value at the input data, it's going to give you the input data. Okay? All right. We have 2 minutes, so I don't think we can do this last one. We'll have to do it next time. Okay? Reverse interpolation. Okay. Thank you.